There is no universally best ZK rollup or privacy protocol. Each architecture makes different trade-offs across security, cost, scalability, privacy, performance, and market fit. The real question is not which design is best. It is, which trade-offs are acceptable for this use case? You now have the toolkit: why scaling matters, how ZK rollups work, where privacy fits, and which use cases benefit. From here, we move from what is possible to what teams must choose when security, speed, cost, and compliance start pulling in different directions. Protocol design is not about finding a perfect architecture. It is about matching guarantees to the job. Each design choice affects several variables at once: cost, speed, security, privacy, decentralization, interoperability, and developer experience. Stronger guarantees usually create pressure somewhere else, such as higher latency, more complexity, or a harder user flow. So when evaluating a rollup or privacy protocol, ask two questions: which trade-offs are acceptable, and which guarantees are non-negotiable? General-purpose rollups are like shared cities: many apps, common infrastructure, strong network effects, and easier composability. That makes them attractive for both developers and users. But they can also inherit congestion, and one-size-fits-most design limits. App-specific rollups take the opposite path. They tune execution, fees, privacy, and user experience around one product or domain. In return, the team takes on more responsibility: liquidity, community, tooling, and distribution. App-specific rollups make sense when an application is unusual enough that shared infrastructure becomes a constraint. Real-time games, exchanges, payments, and identity systems may need custom ordering, predictable fees, or specific privacy rules. The trade-off is ownership. A better user experience may be possible, but the team has to plan for liquidity, bridges, operators, governance, and onboarding from day one. ZK-rollup design often comes down to a triangle: low fees, fast confirmations, and strong security. Users want all three, but teams rarely maximize them at the same time. Lower fees come from batching, compression, amortized proof costs, and sometimes cheaper data availability. Faster UX may come from sequencers or pre-confirmations before Ethereum finality. Stronger security usually means more conservative data and settlement assumptions. The key is to separate what feels confirmed quickly from what is finally secure. Zero-knowledge verification can be cheap on-chain, but proving is often where the real cost lives. That cost depends on circuit complexity, hardware, proving system, transaction volume, and latency expectations. Batching spreads proof generation across many users, lowering per-transaction fees, but it can also add waiting time. Simple transfers are easier to prove than private DeFi or rich identity claims. That means every ZK protocol needs an economic design: who pays, who operates provers, and what incentives keep proofs reliable. Performance is not just throughput. In a ZK rollup, a transaction can feel fast as soon as the sequencer includes it and provides a pre-confirmation. That improves the user experience, but it is not the same as Ethereum finality. The proof still has to be generated, verified, and settled. Strong applications make these states visible: submitted, included, proven, finalized, and withdrawable. That way, users know what they can trust at each step. A ZK proof tells users that the state transition was valid. It does not by itself guarantee that users can see the underlying transaction data. That is the data availability problem. Publishing data on-chain gives users the strongest ability to reconstruct state and exit, but it costs more. External or off-chain data can lower fees, while adding trust and liveness risk. Security also includes bridges, upgrade keys, emergency controls, and governance, because those mechanisms can change how safety works. Zero knowledge does not automatically mean full privacy. At the shallow end, a proof may only show that public transactions were processed correctly. Deeper designs hide selected fields, such as amounts, while still proving the rules were followed. Shielded systems go further by keeping balances, transfers, or application state inside a protected environment. The strongest privacy patterns let users prove identity claims, like eligibility or uniqueness, without exposing the underlying personal data. Privacy is not a simple more is always better setting. Hiding balances, identities, or activity can protect users, but it also reduces visibility for analytics, debugging, monitoring, and accountability. It can make integrations harder when other apps cannot inspect the state they need. Good designs add controlled transparency through view keys, selective disclosure, attestations, allow lists, or eligibility proofs. And the user experience matters because confusing keys or recovery flows can break privacy in practice. Most rollups do not become decentralized overnight. Many start with a central sequencer, upgrade keys, permissioned provers, or an emergency counsel, because that can make launch safer and faster. The important test is whether those controls shrink over time. A credible roadmap defines measurable milestones: more sequencer operators, open prover markets, distributed data availability, stronger bridge security, broader client diversity, and governance that can replace administrator trust with transparent community control. Decentralization is not just about validators or token holders. It depends on who controls choke points. Sequencers decide ordering, which affects censorship resistance, MEV, latency, and user trust. Provers determine how proof generation is secured and whether it is open, permissioned, or outsourced. Governance decides who can upgrade contracts and change incentives. Emergency controls can protect the system during failures, but they are also powerful override mechanisms. The key question is, who can act under what limits and with what accountability? A good protocol evaluation starts with fit. What is this system actually for, and what risks can that use case tolerate? Then judge the protocol as it exists today, not only by its roadmap, fees, latency, data availability, proofs, governance, and decentralization. Most importantly, map the trust assumptions. Who can fail, censor, upgrade, or leak information? Finally, ask whether privacy, compliance, interoperability, and user experience make adoption realistic. Strong protocols align technical choices with real user requirements. The big lesson is that protocol design is trade-off design. Compare architectures by fit, cost, performance, security, privacy, and decentralization path. General purpose and app-specific rollups serve different needs, and each model creates different responsibilities. Next, we shift from technical strength to adoption: distribution, liquidity, developers, education, trust, and finally your capstone evaluation.